Today we're going to be talking about verifying trigonometric identities. What that means is using algebra and trigonometry and what we know about some of the basic identities to show that another identity is true. For example, if I'm interested in showing that my Pythagorean identity, the tangent squared of theta plus 1 equals secant squared of theta, I can apply what I know about my inverse and my basic quotient identities to come up with something that shows this to be true. If I begin by taking a look at the tan squared plus 1 side. Okay, I know that tangent of theta equals sine over cosine of theta. So tangent squared of theta is going to be sine squared of theta over cosine squared of theta. If I'm adding 1 to this, I could say that's the same thing as adding a cosine squared theta over cosine squared theta to my original sine squared of theta over cosine squared of theta. The reason I needed that cosine squared theta over cosine squared theta is I'm trying to add these two things together to make one term, and the only way that I know how to do that is by making some common denominators. In this case, my cosine squared of theta. When I add these two fractions together, I get sine squared of theta plus cosine squared of theta all over cosine squared of theta. I know sine squared of theta plus cosine squared of theta equals 1, and I'm stuck with my cosine squared of theta at the bottom. I also know that 1 over cosine is the same thing as saying secant. So 1 over cosine squared of theta equals secant squared of theta. What we managed to do here was take the left side of the equation and show algebraically that it meant the same thing as the right side of the equation. And that's what we're going to be spending some time on today. Process for verifying identities. In part because it's mathematically and algebraically one of the most challenging things you're going to do, and in part because it ends up being really confusing if you don't have a guide to go by. So some of the problems that you might encounter is that it's very easy to get lost through this process. So the way we're going to avoid that is to only work on one side at a time. This is going to be very important to keep us from losing track of what we're doing, and also to make sure that we don't do anything that doesn't work algebraically. It's also going to be challenging when we have some fractions or some complex expressions. Both of these create problems that are more difficult than they need to be. So if we can find a way to factor or combine fractions, that's really going to help us. Some identities are going to be easier for us to see than others, especially as we move on in this exploration. We're going to see some identities that are really difficult for us to remember and for us to recognize. So a really good thing to look for are our basic identities, which include our quotient, our reciprocal, and our Pythagorean. Along the path of verifying one of these identities, you might find yourself lost or just stuck and not know where to go. And a good way to get yourself unstuck is to convert everything to to the same language, and by that I mean convert everything to sine or cosine. we know that tangent, cosecant, secant, and cotangent can all be written as sine and cosine. So to avoid using some of our less basic identities, converting to sine or cosine can be a real key. Remember, in all of these, your task is to show that two sides of an equation are equal. In other words, for our example, secant squared of an angle minus 1 divided by secant squared is equal to sine squared. Our goal is to make the left side look like the right side. A pretty good habit is to start on the complicated side of the equation. The reason for that is because it's easier to simplify a complicated expression than it is to complicate a simplified expression sometimes. So if we do the complicated side first, and I'm just going to leave my right side alone. You can see I've already added in a few extra lines that we're going to use, and that's going to help us remember to only work on one side of the equation. The first thing that I might do is recognize that secant squared of theta has a Pythagorean identity. It's going to convert to tangent squared of theta plus 1. I'm going to rewrite everything just like we had it. Which provides us with a nice opportunity to cancel my plus 1 minus 1. The second thing that I might remember is that I can write both tangent and secant of theta with respect to sine and cosine. So let's take a look at what that might look like. Tangent squared of theta is going to turn into a sine over cosine based function. So that becomes sine squared of theta over cosine squared of theta. My secant is going to turn into a 1 over cosine based function, which we can take a look at this and realize that we're dividing by 1 over cosine squared of theta. I can convert this to a multiplication problem. Sine squared of theta over cosine squared of theta times, I take whatever I was dividing, I flip it. Cosine squared of theta divided by 1. We can cancel our cosine squareds of theta to 1 and realize that we're left with sine squared of theta. Let's take a look at another identity that we're going to verify. This time we're dealing with a couple of trig-based fractions and a secant squared related identity. So, I don't like the look of those fractions. Let's see if we can combine them into one by finding a common denominator. To do that, I'm going to multiply my right fraction by 1 being 1 minus sine alpha over 1 minus sine alpha. And I'll do similar thing on the left fraction, this time by 1 plus sine alpha. Let's rewrite that below and keep our 2 secant squared alpha the same. So we have 2 secant squared alpha equals, and our left fraction becomes 1 plus sine alpha over 1 minus sine alpha times 1 plus sine alpha. And our right fraction becomes 1 minus sine alpha over 1 minus sine alpha times 1 plus sine alpha. Okay. Let's do some fractional adding. This step I'm also going to simplify the denominator on my fraction by multiplying. And if I notice, I'm doing 1 plus sine alpha times 1 minus sine alpha. That's the same thing as a difference of two squares set up, which will give me 1 squared minus sine squared of alpha. The top of the fractions, I'm going to have 1 plus sine alpha plus 1 minus sine alpha. And I still have my 2 secant squared alpha on the left side. On the top of the fraction, my two 1's are going to combine to give me a 2. Plus sine alpha minus sine alpha is going to cancel out to 0. On the bottom, 1 minus sine squared of theta, which we know is equivalent to saying cosine squared of alpha. Okay. For the next step, we've got 2 secant squared of alpha equals 2 times 1 over cosine squared of alpha. All I did was separate the 2 from the cosine squared of alpha. If I were to multiply these together, the 2 would multiply by the 1 and give me that back. And I know that cosine squared of alpha on the bottom of a fraction is the same thing as saying secant squared of alpha. And I still have that 2 out in front. By showing that the right side of the fraction can be, the right side of this equation can be made into the left side, we have verified this identity.